Welcome! Thank you for joining us on our journey exploring how graph theory is used in several current technologies. This video is presented for IST 230 with Professor Dupak. Our group includes Emilio Cardenas, Brandon Cohen, Anthony Sands, Andrew Snyder, and Jarrett Waters. This is Andrew, and I'll get things started. The origins of graph theory often are traced back to a classic problem called the Königsberg Bridge problem. As originally stated, this problem concerned itself with how to traverse all 7 bridges of a town called Königsberg, where each bridge, or edge of the graph, is traversed only once, and no bridge is left out. In 1735, mathematician Leonhard Euler proved that no such walk through the town or graph existed. In fact, Euler proved that for a walk through a graph to cross every edge only once, there must be either 2 vertices with an odd degree or no vertices with an odd degree. To have an Euler path where start and end vertices are different, then the graph must have exactly 2 odd degree vertices to start and end the path. To have an Euler circuit where start and end vertices are the same, the graph must have exactly 0 odd degree vertices. Instead of exploring the original Königsberg problem much further, how else can we look at the bridges of Königsberg? Let's look at this classic problem from a few different angles to see how graph theory may be applied to modern technologies. Suppose you drive the town's fire truck, and the fire station is in one corner of town. You don't care how many bridges or edges you cross. You need to get to the other side of town by the fastest route possible to put out a fire. Say hello to the Dijkstra algorithm in Google Maps. We'll discuss this in detail in just a few minutes. Now, suppose you deliver mail in Königsberg. You have a list of houses to visit each day, and you want to get the job done as quickly as possible. This premise forms the foundation of several classic graph theory problems, including the traveling salesman. However, this also is used in current technology deployed by UPS and FedEx to optimize delivery routes. Now, suppose you're in charge of bridge maintenance. Bridges wear out based on how much traffic they get. So, you only care about how often a bridge or edge is traversed. Once you start thinking about how many times edges are traversed, or perhaps count how many edges connect to any given vertex, this leads to social network modeling or internet search engines modeling of the connectedness of websites. Finally, suppose the town decides to put up toll booths on each bridge, so each bridge comes at a cost. Now, you need to head across town by the path which has the lowest cost. It is this last example that we'll discuss first in greater detail. But before we get to a modern technology that looks at the cost of each edge, let's explore this concept of the cost of an edge with a decidedly less technological example. This example should help clarify how important the cost of an edge may be when considering various paths through a graph or network. I live in Bryson City, North Carolina, just outside of the Great Smoky Mountains National Park. Almost in the center of the park is Mount LeConte Lodge. This lodge sits on top of Mount LeConte, and the lodge is only accessible by hiking trail. There is no road, not even a service road, to get to the lodge. Supplies are brought to the lodge 3 times per week by the llama train. Yes, you heard correctly. Llamas are used to deliver supplies to the lodge. Staying at the lodge is a very rustic experience, but the experience is absolutely unforgettable. Anyone wishing to stay at Mount LeConte Lodge must decide which trail to use to get to the lodge. Each trail has different highlights like waterfalls or views. But for this discussion, let's assume we are only concerned with how long each hike would take. So, with hiking duration as our only criteria, which is the best hike to Mount LeConte Lodge? For our discussion, assume the trailhead is our starting vertex and the lodge is our ending vertex. Trails to Mount LeConte Lodge include the Alum Cave Trail, Bullhead Trail, Rainbow Falls Trail, Trillium Gap Trail, and the Boulevard Trail, which includes a portion of the Appalachian Trail. Based on mileage, the cost of Alum Cave is lowest. So let's pick Alum Cave. This is what my wife and I did several years ago when we decided to book a night at the lodge and have an adventure. So you begin walking and climbing and walking, and you wonder what you got yourself into. Who knew this would be so difficult? It turns out the Alum Cave Trail gains about 2,700 feet in elevation over its short 5-mile length. You see some amazing views, and luckily you finally arrive. Even luckier, your wife forgives you for not researching the fact that the Alum Cave Trail is the steepest of all the trails heading to Mount LeConte. Clearly, we need a better way to evaluate the cost of a trail or edge, besides looking at only the number of miles of trail length. In 1892, William Naismith, a Scottish mountaineer, devised a simple algorithm for calculating hiking duration of a given trail. This is now referred to as Naismith's rule. Naismith's rule states that you should plan for 1 hour for every 3 miles of trail, then add 1 hour for every 2,000 feet of ascent. So, represent hiking time as h, miles of trail as m, and elevation gain in feet as f. Naismith's rule can be represented as hours h equals miles m divided by 3 plus feet of elevation f divided by 2,000. So, a 6-mile trip gaining 2,000 feet in elevation should take about 3 hours. Naismith was a mountaineer who didn't need to stop for selfies and snacks like I do. So, we need to modify Naismith's rule for a casual hiker. So, we arrive at what I like to call, I'm not a Scottish mountaineer, normal person's rule. This rule says to plan for 1 hour for every 2 miles, and then add 1 hour for every 1,000 feet of ascent. Again, using the same letters and type of formula, we see that a 6-mile hike gaining 2,000 feet in elevation is 5 hours, not 3 as it was with Naismith's hardcore rule. It turns out that this kinder, gentler algorithm is extremely accurate based on how my wife and I hike. So I'd recommend this algorithm to others if you too are not a Scottish mountaineer. If only I had known about this algorithm when planning our Alum Cave Trail hike. Armed with our new algorithm, we see that the Alum Cave Trail cost in hours is much higher than I had originally thought. If we use the normal person's rule rather than Naismith's rule, we see that the anticipated cost of the Alum Cave hike is 5.2 hours. Note that the elevation gain of 2,700 feet contributes more to the duration estimate than the hike length itself. This is a key point for this discussion. It is vital to have a good algorithm for evaluating the cost of any walk along an edge. But what does all this talk of hiking have to do with the current technology? Let's return to Königsberg for just a second. Each bridge is an edge and each landmass is a vertex. So the Königsberg problem may be represented like this. An interesting point about graph theory is this graph may be stretched and flipped in different ways to appear differently. This is just one way of representing the vertices and edges, but it stays somewhat true to the original map. So let's use this representation to depict the graph of the bridges of Königsberg. With a very simple change, our graph of Königsberg is now a representation of a computer network. Each vertex is now a router in a network diagram, and each edge is the fiber optic or copper line linking routers together. To my mind, this network diagram is far too simple. So let's add a few things to make it look like a more typical computer network diagram. We'll start by adding an additional router to make things more interesting. Next, add some access layer switches and a computer and data center as endpoints. Our discussion up until now has been about the cost of traversing an edge between two vertices. It turns out there's a widely used network protocol that, like our evaluation of hiking trails, measures the cost of each edge to determine the best path through a computer network. The Open Shortest Path First, or OSPF, network protocol is an interior gateway link state protocol that measures the costs of each edge to route packets through enterprise networks. There's a lot crammed in that definition, so let's break it apart a little to clarify things. OSPF is an interior gateway protocol. This means it is used inside of enterprise local area networks, or LANs, rather than to connect separate systems like an exterior gateway protocol would. For example, OSPF is used in university campus networks, hospital networks, business LANs, and similar networks, but would not be used to connect these networks to internet resources. OSPF also is a link state routing protocol that keeps track of which links are up and which are down to determine optimal routes. Finally, OSPF uses costs to determine optimal routes. Costs are determined automatically based on the speed of each link, or can be manually assigned by a network engineer wishing to have more control over how packets travel through a given network. OSPF implements Dijkstra's algorithm to find the shortest path between vertices, or routers in our case. Dijkstra's algorithm works by computing the lowest cumulative costs between starting and ending points using all available paths through the graph or network. In this simple example, we see costs placed along each edge. Dijkstra's algorithm systematically checks the cost of each of these edges and then finds the lowest cumulative costs and chooses this path for the routing table. In our case, Dijkstra's algorithm determines that the lowest cumulative cost, and therefore the best route for the routing table, is to traverse the network through the top router along the two edges shaded green. Like our hiking trail example, this path through the network has the lowest cost and will get the network packet delivered fastest. However, as mentioned previously, another element of OSPF is it is a link state routing algorithm. OSPF is implemented in areas. Each area is a defined region or array of routers and links. Within an OSPF area, each router keeps a copy of the link states of all routers within the area. Each router maintains a copy of this link state database, which lists connectivity and costs for each link within the OSPF area. Routers send out link state advertisements to other routers in the OSPF network to inform other routers of changes to the network topology. For example, suppose construction in an area of the building cut the fiber lines running between the topmost and the right router. With the link down, the two involved routers will advertise the change to other routers in the network. Within seconds, routers are aware of the change and new routes are calculated to bypass this edge. In our example, the link state advertisement updates link state databases in all routers, and a new lowest cost path is determined for a packet to travel from our computer on the left to the data center on the right. The new optimal route is now through the bottom router across the two green edges. Most network architects implement several layers of redundancy in a given network. At least among core and distribution layer routers and switches, it is common to find more than one fiber or copper line running between connected components. For example, in our network topology, assume two fiber optic lines are run between each router. Consider these aggregated links, where two physical lines to the router are seen by the router as one logical connection. This is a common network topology. In this case, even if a line is cut so the edge is severed, the link will remain up via the second line or second edge. In our example, if one of the two lines is cut between the top and right routers, the path remains intact, and the route remains the optimal route through the network. In graph theory, this is referred to as K-connectivity. In this case, we are talking about edge connectivity. Assume that we have two lines or two edges running between each router depicted. In this case, the graph is 6 edge connected. It would take the removal of 6 edges to disconnect one of the routers from the network. A network designer also typically plans for redundancy at the vertices. This is achieved using switches set up in a virtual chassis configuration where two switches are linked together and function as one logical switch. With this configuration, we now have redundant edges between each router, and we have redundant routers themselves. Again, this is a common network topology, at least at the core and distribution layers of a network. It is assumed that in our network, access layer switches are connected to each router, even though we only depict an access layer switch on the very left and the very right of the diagram. Therefore, at most, it can be said that our network diagram is two vertex connected. This is because the removal of two vertices, or two routers, will break connectivity to the access layer switches. To clarify this, suppose both of the left routers failed. The computer on the far left is now disconnected, and it has no way to connect into the main network. In our sample network diagrams, costs for each edge are arbitrarily assigned. However, in a functional OSPF system, these costs are dynamically determined based on bit rates of links within the network. Initial OSPF values are determined by routers based on a simple formula. Cost equals reference bandwidth divided by interface bandwidth in bits per second. The typical default reference value is 100 megabits per second, which is 100 times 10 to the 6th bits, or you could say 10 to the 8th bits. Cost, therefore, is 10 to the 8 bits divided by the interface's bit rate per second, and any number less than 1 is assigned a value of 1. Therefore, the cost of a link or edge in a network diagram is inversely proportional to the speed of that link. The higher the interface speed, the lower the cost. The lower the cost, the more preferred the link. Costs in an OSPF network are integer values, where any value smaller than 1 is assigned a value of 1. Therefore, if the interface bandwidth is less than the reference bandwidth, so cost will be greater than 1, the OSPF calculation uses the floor function to round down to the nearest integer. If the interface bandwidth is higher than the reference bandwidth, cost ends up between 0 and 1. In this case, the ceiling function is applied to round up to 1. This could be restated to say, always apply the floor function to the calculation, then if the final cost is less than 1, apply the ceiling function to determine the final cost value. Here we see initial default values in a typical OSPF network. For simplicity's sake, the 100 megabits per second reference value in the numerator is written as 10 to the 8th rather than 100 times 10 to the 6th. However, values in the middle calculation column are written intentionally with exponents to call out megabits versus gigabits in the denominator. Clearly, 100 times 10 to the 6th could be rewritten as 10 to the 8th, for example, but 10 to the 6th is a megabit, so at least for me this is easier to read. Default values pictured assume a reference value of 100 megabits per second, sometimes called fast Ethernet. Clearly, above 100 megabits per second, the cost formula no longer distinguishes one link speed from another. A network engineer can modify router settings to use a different reference value to allow OSPF to distinguish speeds above 100 megabits per second. As a reminder, these costs are used by routers implementing the OSPF routing protocol to calculate the shortest or lowest cost route through a given OSPF area. The lowest cost path is always preferred as it has the highest speed. We started our discussion of the applications of graph theory to modern technologies by talking about things that aren't modern technologies at all. We talked about bridges in a small town, and then we talked about the importance of measuring the cost of edges in a graph by talking about hiking trails to a lodge in the middle of the Great Smoky Mountains National Park. But these discussions of non-technical topics led us to an understanding of the open shortest path first interior gateway network protocol. We learned about Dijkstra's algorithm and its method of computing total cumulative costs of a path through a network. We also learned about how OSPF uses link state databases and link state advertisements to quickly converge and work around link state changes where an edge or link is removed from a network. We also talked about how network engineers use the connectedness of a graph or computer network to design networks for resiliency and redundancy. Well-designed networks have built-in fault tolerance, where some edges or vertices can be removed without impacting connectivity. Now that we've talked about routing network packets through a computer network based on some concepts of graph theory, how else can graph theory be applied to modern technologies?
So far, we've talked about the different algorithms used in graph theory, but now let's talk about the applications that graph theory has on our day-to-day life. So today we'll be talking about Google Maps in particular, but different applications such as MapQuest and Maps use the same type of technology. So instead of determining the best path for TCP IP packets throughout a network, suppose we need to determine the most efficient route for a person to drive their car, walk, or take a hiking route to get from point A to point B. So for Google Maps, let's go over a little bit of history first. It was introduced February 8th, 2005, after being acquired from a startup called Where2 Technologies. This particular mapping system uses the Dijkstra algorithm. Let's talk about why the map looks the way that it does. So take the map below, for example. This is the type of map you would see where it describes the distance to get from one place to the next with multiple routes to get from one place to the other. For example, if you wanted to go from Chicago to Boston, you could take the route from Chicago to Philadelphia to Boston, you could take the route from Chicago to New York to Boston, or you could take Chicago-Detroit to Boston. When looking at the number of miles associated with each distance, you can clearly see that the best route from Chicago to Boston is to go from Chicago to New York to Boston. This type of node arc system is used by Google Maps. Each of the cities on this map would be considered a node, and the lines between them would be considered the arcs. Although the distance isn't the only thing that we are concerned with, when trying to map out our trip for ourselves, to be the fastest, you're concerned with the presence of traffic lights, the size of the road, the speed limit, and the traffic on that road. Google Maps accomplishes this by giving each line or arc a weighted value with all the concerns in mind. So if this arbitrary value, say you're going from Chicago to Philadelphia to Boston, you could give it an arbitrary value of 10. And you're going from Chicago to New York to Boston, it's giving an arbitrary value of 5. Or you want to go from Chicago to Detroit to Boston, and that's given an arbitrary value of 8. It's clear that the best case scenario for a time would be to go from Chicago to New York to Boston based on the lower weighted arcs. So now let's talk a little about Dijkstra's algorithm. As previously stated, the arcs between two nodes are given a weighted value to determine how fast it is to travel from point A to point B. What the algorithm does is it looks at the weighted graph and finds the minimum path it takes to travel from point A to point B. When dealing with multiple arcs, it takes all the values of the arcs in between the two nodes and tries to find the least sum, therefore finding the fastest possible route. So this algorithm, paired with Google satellite technology, Google Maps is able to find the fastest possible route between two nodes with whatever you're doing, whether that be going for a walk, taking a drive, or taking a hike. So now let's take a look at route optimization.
Talked about how graph theory is important in our daily lives with apps such as Google Maps and other apps used to get from one location to another quick by finding the shortest route between the 2 points. Graph theory is also used in businesses such as FedEx or USPS or any businesses that are focused around delivering items. I'm going to be talking about route optimization, which is widely used by these companies. Route optimization is the process of finding the most cost-effective ways to get from one point to another. Many think that this means finding the shortest path to get to the destination or the fastest route between 2 points, but route optimization takes it further than that, by considering other factors when generating a route. Some of the factors that are considered in route optimization are the number of turns that are going to be taken, how many left turns will be made crossing the line of traffic, as well as how the traffic is throughout the day, and several other factors. This is done using algorithms, since doing this manually will be a big waste of time, since there could be several thousand different ways to plan a single route, and many more when dealing with several different vehicles. This process is specially designed to find the most effective route when making several stops, unlike Google Maps, which is more designed to get from point A to point B. This is especially useful when dealing with several different drivers making deliveries. Route optimization stops there from being several different drivers to end up in the same location, costing the business time and money. There are several benefits that can be had using routing optimization programs to plan out delivery routes. Some of the benefits include cutting down on gas usage, as well as reducing the time that the vehicle is going to be on the road, which help with reducing how often the vehicle will require service, as well as reduce the potential for any accidents. Help with any last minute changes by quickly modifying the routes, allow for more work to be done in a single day, which also helps make sure that the items being delivered get to its destination on time, which helps with improving customer satisfaction. It also helps the drivers by making sure the drivers won't have to make deliveries that are much further away than their other deliveries, which helps keep the drivers safe, since there won't be a need to rush to keep up. These aren't the only benefits to be had when using route optimization. There are many more. Up next, another group member will be talking about social network mapping. Thank you.
I'm Anthony Sands, and this is the conclusion to our presentation. Here are the references that we have used throughout the process, and I wanted to lastly thank everybody in the group, wanted to thank everybody in the class, wanted to thank Professor Dupac for this amazing opportunity. I had a fantastic time editing this video together and being a part of this group project, and this has been super informative and super fun and super just interesting start to finish. And I hope that you all appreciated it and enjoyed our presentation.